So I think it's clear that, as Professor Bunda said, that education and people are very much at the heart of everything that we're building here, and certainly at the heart of today. In fact, as Arkady alluded to earlier, the nice quote in a breakfast we were holding with some local media just earlier, people are the cornerstone of the ecosystem we're building. So if we want to understand where AI is taking us, we need to hear from the people who are actively pushing the boundaries. And with that, I would like to introduce Max Welling, who's one of Europe's most respected AI scientists, the co-founder of CuspAI, and on the side, a professor at the University of Amsterdam. CuspAI is applying machine learning to some of the hardest problems in materials discovery. So Max's work sits right at the intersection of rigorous science and real-world impact. Max, please, the stage is yours.
Yes, thank you so much for the introduction, and very happy to be here today. And I'll be talking about reimagining scientific discovery in the age of AI. So first, to get in the mood, I'll just first show you a little PR video from Cusp about materials discovery. I hope I'm not in the way. See it. Let me talk about what I see coming as the next big revolution in AI. Of course, we're now going through a revolution. Let's, in the sake of history, go back to the 1700s. In 1700s, there was the Industrial Revolution, and there people invented machines that would replace human and animal labor by machine labor. Of course, the steam engine was incredibly important. And today, we are going through another AI revolution, which is the revolution where we replace human intelligence, or at least, let's say, enhance human intelligence with artificial intelligence. And at the very core of all of this, as I will argue, and also in the wake of this, there will be a third wave of innovation, which is physical AI, and sort of related to that is an innovation wave to generate new materials. So we start from data, which were either generated by computation or by experimentation. We then have an AI-powered design engine, which is going to be CuspAI, or is currently already CuspAI. And then we're going to design all sorts of new materials in many sectors, like let's say aerospace, solar, battery, or semiconductors. And so you can now think that these revolutions will actually feed off of each other. So the Industrial Revolution resulted in the AI revolution. The AI revolution will power physical AI and the design of new materials. And then from there, new materials will power the AI revolution again, because we will get to new sources of energy, which are needed for data centers, in the, for instance, new solar technology, which are currently being developed, but also, of course, new semiconductors and chips. And then from new and more powerful chips and more availability of cheap energy, we'll, of course, be able to generate more AI and, again, design new chips and materials. So this will be a virtuous cycle that will accelerate. And we wish to be at the core of that. Now, what has happened, what has changed, and I think here Nebius is, of course, very important, which is this curve here that is going upward. So the availability of new compute and fast compute has moved materials innovation first from fully experimental, which is more or less just trying out a lot of things in a test tube and see what sticks, to data analysis, generating a lot of data, and then analyzing this data with statistical methods, to a new way where we actually simulate the entire material and chemistry in a computer. And increasingly, we can now actually do the experiments which you used to do in a test tube. You would do them actually in silico. And this will accelerate, and it will help us do less experiments. Experiments will also always be very important. It will enable us to do less experiments and do more in compute. And so this, I think, is where a lot of the computation is going to sit. And so maybe good for Nebius to think about whether they want to support that. It's not only GPU, it's also CPU, it's also ASICs, it's different kinds of compute. And so what I think is a sort of a good way to think about how the paradigm is shifting. So just imagine you're a company that designs drugs. And so here I design a new drug, and I'm thinking medical drug, of course, and I'm thinking, is that a good drug? And so what I will do is I will try to simulate that drug in my computer, or I do an experiment. But in any case, I'm spending money and energy in order to assess whether this is a good drug. And let's say this was a bad drug, it didn't work. And so I come up with my new candidate. And now, if I would follow the normal paradigm, I would have to go through the entire process again. I would do all the computations, the MD simulations, the quantum calculations. I would have to do them all again. And that's a waste of energy. Because this has actually delivered us information. And this information we should all store in a big database. And then from the database, we train a neural net. It's a bit blurred here, but it's a neural network that now contains all the information which was originally in the database. And now we are going to use the neural network to accelerate the evaluation of the next drugs. We can either do this by machine learning force fields, which I will talk a little bit about, which accelerate the evolution of these materials in a computer, or direct property predictors, where you don't do any simulation anymore. You have just gotten enough data to directly predict the properties that you're interested in. So now this phase can be very fast. If this evaluation phase is very fast, you unlock search. So you can do you can try more and more candidates and evaluate them cheaply. Okay, so let's do a little bit of, sort of chemistry in order to understand what the real challenge is that we are facing. A molecule, in a very simple representation, is just a bunch of beads of different type, like oxygen and hydrogen and carbon, etc. And they are held together by forces, different kinds of forces, but the most important ones are quantum mechanical, because, let's say, electrons are shared, and so they're in some orbit around these atoms, and they hold this together. So we have the forces. And then in order to evolve this forward into the future, which molecular dynamics is, in order to compute the properties of this molecule, we can just use Newton's equation. So that's around 1678. So that's very old math, very easy math, until you realize that you need to compute that force. And then you figure out, in order to compute that force, you need quantum mechanics. You need to solve the Schrödinger equation. So here we are, Heisenberg, 1924. We need to solve the Schrödinger equation. If you have anywhere beyond 10 electrons, this is totally hopeless. You cannot do it. And so people have computed alternatives. I will talk a little bit about this, like DFT calculations, but it's still very expensive. And then you're starting to evolve. So, you can evolve, but you figure that In fact, you can only do a nanosecond at most of simulation, where many of the things that we want to understand live at much larger time scales, like folding maybe happens at microseconds or something like this. So it's still very challenging. And moreover, it's chaotic. So it's like you can evolve, but of course, it doesn't mean if you don't know the initial boundary conditions perfectly that you will actually get an accurate answer. So then we get into modern sort of physics of 1961, where people studied chaotics. And then, of course, if you want to search in the space of molecules, it's even worse because the space is literally enormous, like almost infinite. The number of ways you can make these molecules, and then you need to be very smart in how to move through that space in order to find the molecules with the right properties. And so people have built a lot of powerful tools in the chemistry and physics literature in order to assess materials and chemistry. And for instance, at the very smallest scale, the slowest methods, the people have found ways to solve the Schrödinger equation. And then we go up to DFT, which is density functional theory, which is an approximation to quantum mechanics. Then we go to molecular dynamic simulations with the classical forces. We go to coarse-grained simulations, particle-based simulations, coarse-grained particle simulations. Then we go to classical density functional theory, and then continuum methods, which are basically PDEs. And then what the interesting thing is, so we call this simulation. And for each one of them, there is a AI or machine learning equivalent that will accelerate this sister method by many orders of magnitudes, sometimes 3 to 4 orders of magnitudes faster. And that's what we call emulators. So these emulators are methods that solve the same equation but have used neural networks inside, trained on lots of data to accelerate this, right? And so we have quantum Monte Carlo, which I'll show you in a minute, quantum DFT machine learning functionals, which I'll show, machine learning force fields derived, machine learning force fields, which I'll show in a minute. So each one of these, including all the way up to PDEs, where people have now trained machine learning surrogates to massively accelerate this. So here's an early example. This is from DeepMind. This is the Fermi net, and there's later also a Pauli net. This is, you take in a configuration of a molecule, you push it through a neural net where you respect all the things from quantum mechanics, like exclusion principles and all these kinds of things, and you predict a wave function, and then you use the wave function to compute the energy, and you want the ground state, so you minimize the energy. And this was very successful. It accelerated solving the quantum Monte Carlo method many orders of magnitude faster. And so more recently, there was an alternative to DFT, which is a Nobel Prize winning technique to simulate quantum mechanics in molecules, where basically this team from Microsoft has trained what's called a functional from lots and lots of data that you can minimize, and then you can actually do DFT level, accuracy level calculations, but with a machine learning force field. Sort of with the machine learning functional. And these are the force fields. These are actually very powerful. I predict this could be a Nobel Prize at some point all in its own right. And the idea is here that for instance, there's models like UMA from Facebook, and there's MACE from the University of Cambridge. And these are models where you compute using DFT a lot of data on these forces of these molecules, and then you train a neural network to predict the forces directly. And these you can use then to simulate pretty large molecules at the level of DFT. And so you can get to the size of what typically only classical force fields can do, but at the speed, but at the accuracy of a quantum mechanical DFT calculation. And this is really revolutionizing the field of computational chemistry as we speak. And of course, this we all know. This is folding. This is a machine learning methods trained on lots of data to predict the three-dimensional structure of a protein. Again, a machine learning method to solve a chemistry problem, also a Nobel Prize in 24. And then finally, I want to highlight this one. I've been working in this field also for a while. This is weather prediction. So at Microsoft, when I was working at Microsoft, we had a model called Aurora. Actually trained not so bad. It was on 35 A100 GPUs for about 3 months. So this is where actually what you can do with that level of compute. And what the interesting about this particular problem of weather prediction is that the meteorologists have been really good at saving all their data. So there's literally petabytes of data publicly available on the state of the atmosphere over time. And you have to solve this PDE, which is called the Navier-Stokes equation, plus a whole bunch of other equations. And so you replace the numerical solvers with neural networks. And then the surprise was that not only can you predict the weather 10,000 times faster, it actually also is more accurate because it's trained on all this data. And that was a big surprise. The meteorologists did not want to believe this when all this started a few years ago. They said, we are doing this for hundreds of years. You're not going to disrupt this field with a neural net. But it was disrupted, and now they're all integrated in their software stacks. So these are great examples of how AI is disrupting this field. Here's another one. This is from Microsoft. We're also building exactly the same tool. We have already built exactly the same tool, but it's a very nice visualization from the Microsoft. You cannot quite see it here very well, but anyway, that's the Microsoft team. And this is the same technology that generates videos and images and slides on your computer. It's exactly the same tool that's now being used to do something truly useful, which is generate a molecule, let's say, with properties that you may want for a new battery or for a new drug, right? And so here we go. We start with noise, and the noise gets transformed into a, in this case, crystal structure at this speed. And you can literally do thousands of these, all with different properties. And of course, once you've generated them, you can then put them through your evaluation stack and see how good they really are before you actually put them to an experiment. And so how does this work? I just want to dive a little bit in the physics of this, or the kind of the engineering of this. How does this work? It's very interesting stochastic thermodynamics. So it's a non-equilibrium thermodynamics problem that you're really solving. So you start with a structured object, so like say an image, and then you let it evolve over time in the direction of physics, which means that entropy will increase and it will get destructured into noise, right? And that's just an equation you can solve as an SDE. And then you monitor this process step by step. You say, what happened when I went from here to here? And what happened when I went from here to here? And of course, you're trying now, you just, by monitoring, you say, what do I need to do to invert time? So what if I would have this, what would I have to do? What forces would I have to apply to turn this into this? It's like you have an egg, you throw it on the floor. That is normal physics. You never see an omelette turning into an egg. But if you look at the movie many times, you could derive all the forces that would turn an egg on the floor into an egg in your hand. And this is exactly what we do. It will cost, of course, a lot of energy to do it because it's against natural physics. And this is what we do at Cusp, for instance. We have these types of models for this beautiful class of molecules, which are called metal organic frameworks. These are the molecules that won the Nobel Prize this year in chemistry. And they can be used to take carbon dioxide out of the atmosphere, which is a truly important problem that humanity needs to solve. Because by 2050, we have, hopefully we are not emitting any carbon dioxide anymore, but we will still have to pull about 20 gigatons a year out of the atmosphere. And we have not solved that problem at all. The other thing you can do with it is extract PFAS from water in order to clean the water, which is a project we do with a company called Chimera. And here's another tool that we've built. This is a tool that's very heavy on compute in data centers. This is called Grand Canonical Monte Carlo sampling. It's a Monte Carlo sampling technique. Here's one of these beautiful metal organic frameworks. Here's a carbon dioxide molecule. And what you need to do is you pop in and out of these molecules, and then you wiggle them around according to physics. And then you see when they stick to the side. And you want to understand how many stick to the side at a particular pressure and temperature. So here's the pressure. You put it up at a particular temperature. And you want to say, if I increase the pressure in my metal organic framework, how much more of the CO2 will stick inside this porous medium? And you want this curve, because once you have that curve, you can optimize the metal organic framework for real purpose. And so this is the tool that we developed. Actually, this is in collaboration with NVIDIA to make sure that this tool runs really fast on GPUs. It will be released very soon. So actually next week I'm going to iClear and we will openly release this particular tool. And I hope Nebius can also host it on their machines, because it is actually a very heavy computation that can take days to do this. And so on GPUs now we can do it much faster. And you can enjoy the amount of compute that's being done on your GPUs. Okay, so now I want to say something. So this is kind of the introduction to the big revolution that's coming in my view. This is going to take up huge amounts of workloads in the cloud, I think, in the future. And we are trying to get it onto the cloud as CuspAI. We're trying to bring these more traditional companies to do their computation in the cloud, because that would help us design materials with them. And so we started CuspAI as a company to build the platform, the digital platform, to design these materials. We are currently in the process of connecting the digital platform to the physical experiments, the high throughput physical experiments, so that we can actually also verify and get feedback from the experiments. And so we believe that many of humanity's challenges in the future, like semiconductors, but also energy transition that we are going to make, are really rooted in materials problems. And if we want to very quickly design new materials, we need these kind of digital tools. So the company that we've built so far, it started in 24. We've raised 220 million up to date. We're about 50 people strong. We're operating from Cambridge. It's headquartered in Cambridge. We have a second largest group is in Amsterdam. London, there's also a big group. Berlin is a big group. We're now expanding into Singapore. And then more recently, Tokyo and San Francisco. And we are backed by, of course, good people and venture capitalists. And so this is the core leadership team plus a sort of representative from our technical staff, which is, of course, where all the work really happens. So Chet Edwards and myself started. So he's the CEO operating from England, and I'm the CTO. And then, I won't go over all these people, but maybe highlighting Aaron, who joined recently, who is a very well-known scientist in material science. And maybe interesting for you guys also, Alessandro de Maria, who is our chief architect, our ML ops person, that if we ever work with Nebius, that's the person that you will have to deal with. And then this is our advisory board. It's a very distinguished advisory board, also because they really want this. We believe we do good things with AI. We only build things that will help the world forward, in particular climate change. And some of them are super active. Actually, I have a very good relationship with Martin van den Brink, which is a great honor for me because he's of course being the CTO and president of ASML, and he's actually the brain behind the ASML machines, and he's helping us also shape our company. And Lord Brown is Chet's sort of buddy to think through the business side. He's the former CEO of BP, British Petrol. And of course, Jeff Hinton and Janne Koen I know very well on a personal level. And then Kristen Persson actually runs the materials project, and Verity Harding is working for the UK government on policy. Okay, so we work in different areas. So the first one is surfaces and separations. This is materials that bind and separate and protect, like adhesives and membranes, barriers and coatings. The second one is catalysis and conversion. So materials that drive clean energy, carbon conversion, and sustainable chemical transformation. Catalysis is a big one. So ESAF is a big one here. We all need ESAF these days because our kerosene is going to slowly becoming depleted these days, and it's going to become very expensive soon. So maybe these technologies where you create kerosene from thin air, literally you can create it from thin air, but you have to put the energy in it, will stand a chance to be developed. And then semiconductors, both for PV, so both for developing new solar panels like perovskite layers, which people now put on silicon in order to improve their efficiency, as well as for a chip. And so, yeah, so this is the materials engine that I'm going to talk to you a little bit about. So, so this is the way we envision one should do materials design. And so you start, so the old way is a bunch of scientists sitting in a room thinking about a problem, then hypothesizing what would a good material be, maybe read some literature about it, and then designing an experiment, and then do the experiment, and then look at the data and repeat, right? And that's very slow. So the way we imagine doing this, or what our platform actually is doing, is it starts with a query. So you just, it's like vibe coding, right? You just say what you want in language. And maybe you be a bit more precise about all the properties that you want. That's given to a search agent, where you will see in a minute. And the search agent will make a plan, like an optimized orchestration plan. So, okay, I'm going to use these tools in this sequence in order to come up with a good material. And so maybe the first thing it will do is go to the database and say, we have actually a lot of contracts with big publishing houses where we have purchased licenses for their data. And so it will go to the database and try to find materials that are already out there that maybe are fit to purpose. If not, it will then go to the generative models, and it will start to generate many thousands of candidates. For our last campaign, we ran up to 500,000 candidates through our generative models. And then they go through a funnel. So the first, we have very fast property predictors, which will sieve out everything that's doesn't look promising, or is not physical, or is not stable, or is charged in some way. So we can all sieve this out very quickly. And then the more expensive the simulation and evaluation tool becomes, the fewer are sort of left in this kind of competition. And then we typically go to an experiment. We want to actually go to experiment very fast, depending on the speed of the labs. If this is a high throughput lab, a self-driving lab, you can do very many experiments very quickly. And so you would do less digital and more experiment. And if the experimentation is expensive, you'll try to do as much computation as possible before you go to the lab. I think of a lab more or less as another way to compute. It's not a digital compute, but it's natural compute. It's a bit hard and clumsy to program, because you have to set up an experiment. But in the end, you're doing a computation done by nature. So this goes around, the agent will inspect what it has done. If it's not good enough, it will generate more stuff. And importantly, every time, in every phase of this, data gets generated, insights are acquired, and they all go back into our database, because we want to amortize, so next time we can go around faster. And so typically we go to a customer, the customer specifies what it wants. We do candidate generation, we do simulation, we do synthesis and testing, experimental feedback, and we go round and round. And this is what our platform looks like in a little bit more detail, and I'll show you in a minute a demo. What happens is you start with a prompt. It goes to an agent. The agent typically goes to the literature, which is proprietary data, literature data, and customer data for a particular project. And it will then start to engage all sorts of tools in some workflow in order to find the right material, which goes from property predictors to MD simulators with force fields. It can decide to train or fine-tune a force field. All these things are happening. It then goes to experiment. It comes out with a candidate, and then it cycles. So here's a little demo of how that works. So here we type in something, so you'll now see what it types. It says, generate high-porosity MOFs with an electronically inert metal node, suitable as a low-K dielectric and semiconductor interconnect layers. Relax these structures, check if they are valid using MOF checker, and compute void fraction. Okay, that sounds very technical, but our agent understands this very well, and now it starts planning. So it says, okay, this is the things that I'm going to do. Right, I'm going to generate MOFs, relax structures, validate them, compute void fraction, and then it's going to do these things. So it's first going to generate materials. So this is our generative model that is now generating live, basically not live, real time, generating these molecules. It was accelerated when it blurs. It accelerates a little bit because it takes a little bit more time than we can do here. Okay, and it generates a number of these structures. I think this is around 17 or something like this. And now it's checking. So it's checking with a tool called Zio++ that's designed for MOFs, or if these generated candidates have the right properties. And this is real time, so this can go very fast. These property predictors are super fast. So there they go. It's running through, for each one of them, it's running through this analysis. And then it's now going to report. So it says, okay, collect the results and then summarize the findings. So in this case, we haven't done the expensive campaigns or the large MD simulations, which could take days, we haven't done. But now we're going to write a report. And here is the thing. So it finds actually this one doesn't work after all. These ones are fine. And then it ranks them in terms of how promising they are. And now it's going to create a report, and then we can actually inspect them. So we go to this tab, and we say, okay, this is the top performing candidate. Let's have a look. Okay, this is the MOF that it has generated. So these are the metal nodes, and these are the linkers in between them. And yeah, so you can just visually inspect this particular top performing node. But so now we still need to make it. So now it's going back into the literature and say, find for me a synthesis recipe. So it goes in and sort of looks at similar MOFs. So we have a search tool that tries to find things that are very similar than the one that we've generated, looks at their synthesis recipes, and then starts to suggest ways to synthesize this particular MOF. And that's what it will do now. And then here come 2 possible ways to synthesize this. And of course, you never know until you try. We haven't tried this, but our chemists say that this is a not unreasonable suggestion of how to generate these particular metal organic frameworks. Okay, and then we actually made the metal organic framework. So this is actually made by us. They're very pretty. They have all these different colors because these different metals have different colors. So we made it in a lab and we sent it to the US in order to test them in a rig. So this was the very first thing we did. They worked, but not better than current state of the art. So we're not commercializing or anything. This was just for us to get through the whole pipeline once and sort of test every piece of it. And that brings me to my conclusions. So we're all, very fascinated by digital AI, which is chatbots. I think there's a new wave coming, which is physical AI. And this is connecting the brain, the digital AI, to the physical world. And this will be a huge pain because the physical world is with lots of friction and it's slow. But it has to, there's also a lot of promise. And so one of the things that we do is automatic experimentation, where we also need to connect the digital brain to the physical world, which is the chemistry experiments. And maybe interesting for Nebius is like physical AI will probably require different kinds of compute than pure LLMs, right? And so LLMs are all transformer-based, and GPUs are perfect for that. But the type of compute we would need for this could be quantum DFT, which is run on CPUs. Or I would actually think there will be new ASIC, new kinds of chips, which will be designed to, for instance, run many of these workloads. And also because these humanoid robots and phones and all these form factors and drones will need to run these AI, maybe also things like edge compute will become quite important. I actually worked for Qualcomm, where it was very big on edge compute. And I think that strategically, materials are at the root of these problems. And this is very important for Europe, as it wants to become sovereign and build a sovereign stack. Many of these materials, are the ones that will create dependencies on others. Like very clearly chips, we need our own chip industry, which we do have, but we need to enlarge it. Rare earths is a very typical one, of course, which is a core material problem. How do you extract those from the ground and also from the sea? The energy transition, obviously, like batteries, solar panels, all these kinds of things, are a core material problem. And then climate change, how do we get carbon dioxide out of smokestacks or out of the atmosphere? And I believe that Europe can still play a very significant role in physical AI. Maybe they missed the boat sort of on LLMs. Although I never believe we should completely give up. But, there is a new wave coming, and I think Europe is pretty good in robotics and manufacturing. China is going very, very fast in this space, but it's not completely run. And I think Europe should play an important role in this physical AI, and therefore I think we should also invest. And I'll end there. Thank you very much.
Max, thank you so much for this amazing talk and sharing us what you do at CuspAI and what's going on generally in AI for science, including material science. So anyone who want to ask question from Max, we have 15 minutes. Just scan this QR code or any QR code as mentioned before, and type your questions, and I will be happy to ask them from Max. So maybe to start, you worked a lot in your research on models that related to structure, yes, and we have a beta lesson at the same time that's compute, often beat sophisticated models. How do you see it now and envision now, and specifically in your current domain?
So the compute story and the bitter lesson works if you have an enormous amount of data, right? But in this domain, the data isn't abundant at all, except for material science, where I think it does work. So in material science, you have seen that models that are just black box transformers trained on this enormous petabytes of data will outperform models where you try to put in physics priors. But this is not true for all regimes. So if you go to chemistry, you need to compute DFT data, which is very expensive. And it's also typically valid for a particular subset of materials. So the approach we take there is, for instance, with Meta, we are working on, and we have worked on generating these, what you call foundation models for chemistry, which are these machine learning force fields. That would work okay-ish for all of molecules and materials. But then when you actually want to do an actual simulation in a particular material, you will then have to fine-tune that for a particular problem, like a particular material class. So you can make it much smaller and much faster. And there, physics priors do help a lot because you're training on pretty small data sets. In fact, I would say even the bigger models like MACE and UMA are all, for instance, they have equivariance and symmetries built in. So there's definitely some symmetries, about some priors of the world that you can put into these models. But in the end, it's a function of how much data you have.
Okay, great. Thank you so much. And we already have some questions, and we may start with a question from Olga. So how do you benchmark the results you obtain with CuspAI in comparison to other agents and solutions?
Yeah, so we emphasize validation a lot internally. Now, some of them are quite easy, right? Because you have a data set of properties of molecules, and then you can just train your property predictors. You can just do the typical sort of validation, out of distribution validation testing. For instance, Bayesian optimization or searching for materials, it's a little harder. And for an interactive chatbot, which we're also building for a chemist, it's even harder to validate. But we do have LLMs validating and testing other LLMs, for instance, to this typical paradigm. And ultimately, we also want to do A/B testing with chemists that are using the models.
Cool, thanks. And the most voted question right now is from Vlad from Stevens Institute. So neural nets gain enormous efficiency by compressing regularities, but average loss smooths over the tails. So when extremely rare but valid events are the signal, like for example, orphan, rare disease, crashes, fraud, etc., how should we think about modeling that?
Actually, it's a great question. It's been on my mind quite a bit. So the way we've approached it, actually, recently with a PhD student who's now also in CUSP, which is Dario Korsia, we have built models that would not just predict the answer, but also the uncertainty in the answer. So basically, it understands when it doesn't know what the actual answer is. And so what you'll see, both in PDEs, but also in machine learning force fields, it makes predictions, and every time you move it outside of the domain where it hasn't seen data, it will increase the sort of the window in which it thinks the answer lies. And then if this window is too large, you just should stop or start to take more data in and stuff like that. So I think uncertainty prediction is going to be super key there.
Great, thank you. We have a question from Daniel. Do you use in-house LLM for agents, or some closed source like OpenAI, Anthropic, or maybe you fine-tune probably some of source models?
So we do both. Mm-hmm. So the one that you've seen here was just Anthropic with providing, providing Claude with a very large number of data to inspect and tools to use. But we're also training our own open weight models and fine-tuning those, and then comparing the two. And so, yeah, so I think we do a mixture of those. We are currently pitting them against each other and looking at the advantages and disadvantages.
Great. So Emil's question, what is happening now at the stage of candidate prediction, like AlphaFold in drug discovery, but in subsequent stages, such as wet lab experiments?
What's happening with us for subsequent?
This question, like, how I understand, like, what's actually going on in a wet lab experiments based on your predictions?
Yeah. So what we do is we build an ecosystem. Yeah. So what we do is we call this foundries, where we connect compute. We're talking to compute providers, and we should talk to Nebius as well about being part of that ecosystem.
We'll be happy.
Yeah, good. For instance, in order to get chemistry companies to do compute in the cloud, we want to catalyze that, and so we provide them with some free compute or low-cost compute. And then there is the experiment. So we have contracts with A*STAR Labs in Singapore. We talk to a lot of others like DTU and University of Cambridge. There's a whole bunch, various labs in the Netherlands as well, where we work with them to connect our platform to their experimental setup. And so we want to standardize this so it is quite easy and painless the next time around. And that's creating a network of labs. And every lab is different because if you target a new material class, you need a new setup, a new bunch of machines. So that's why we think we should talk to many of these labs, but everyone connect them to our brain, let's say our CUS platform. And then we get with the customer and say, our customer, I want to find a new catalyst. Okay, so we go to DTU because they have the lab to do this, right? And then we go through a campaign where we predict catalyst, they make the catalyst, provide feedback until we get to the catalyst design that we want, and then we go back to the customer and basically sell it back to the customer. So that's the way we do it. The experiment is always incredibly important. We're not doing it in-house because there's too many different labs you then have to maintain. We're doing it in an ecosystem play.
Okay, thanks. And there's a question from Vladislav, like how susceptible are the described models to train test data drift? So, for example, can it lead to like errors during model predictions for the properties of materials that are not actually present in the training data set?
Yeah, this is of course true for any machine learning problem. I think the most vivid example to me is you can be very proud of your weather prediction model, but then if you talk to a climate scientist, they are not so keen to use your models because they say, well, you've trained it on a particular atmosphere with a certain amount of carbon dioxide in it. If you're not using physics, you'll run outside of the domain where you're trained and becomes unreliable. And I agree with this. So you do have, but the idea is to have a sort of an active learning loop based on uncertainty. So you try to predict if the uncertainty goes up, you figure out that you're not doing well in this space, and then you start to collect more data in this space in order to fine-tune your models more. This is a continuous effort that we'll have to always go through. Every new problem, we'll probably have to collect some data and fine-tune our models to work there.
Great. And I think the last question from the audience now is we run out of time. So you mentioned the possibility of developing like rare earth minerals, like alternative to them. But when you find these candidates, like, can you actually produce them from the common materials? Would it be a problem? Is that a question from Toby?
Yeah, so at this point, we are not actually doing this, but it's on our radar. The companies we've talked to that are interested in this, for instance, this was not necessarily about finding alternatives, although there's quite a bit of activity, for instance, for permanent magnets to come up with alternatives. This is about different ways of mining it. For instance, lithium, there's a lot of lithium in the sea, actually, in seawater, especially close to mountains and where sort of rivers stream into the sea. But it's, of course, very dilute. And so better ways to very sort of target a particular molecule at a very low concentration, extract it out of the water in a very cheap way, because it has to be cheaper than digging it out of the ground. Those are very nice problems for this platform to solve.
Great. And you also mentioned during your talk about diffusion models and like how generative AI and stochastical thermodynamics can be combined. And now I know you published a book about it. Can you, like, considering our public, like researchers and engineers, are like, what are the key ideas? Will it be interesting for people to read it?
So the surprise to me was that the mathematics behind stochastic thermodynamics, which is actually a very new theory, it's still very actively researched today, or sometimes called non-equilibrium thermodynamics, and many of the things we do in machine learning, not just diffusion models, but in the old days, also variational inference methods. The mathematics behind those is very similar. You can write down a free energy, which is the energy minus temperature times entropy, which holds both of these fields. And in one field, it's like you minimize that by first minimizing the variational distribution, which would be the equivalent of relaxation in the physical world. And the other one is to update the parameters of your model, to learn a model, and that the equivalent of that is doing work or controlling the Hamiltonian of your system. This is just one analogy. There is many more, like, for instance, annealed importance sampling, which is developed in our field by Radford Neal, turns out to be the same as the Jarzynski equality developed in this non-equilibrium field, stochastic thermodynamics field. There's many more where you can, and then diffusion models is maybe the best one. Diffusion models, actually in the original paper by Soldikstein et al., it was already mentioned, the relationship with non-equilibrium thermodynamics. It literally is running a sort of a system under diffusion in one direction and then trying to learn how to invert the movie in the other direction. And that is literally trying to control a system to go back from an end state to a begin state. And what we've done recently, for instance, is use all these ideas to compute the free energy difference between two distributions. So if you have a molecule in one state, like an unbound protein and a molecule, and you want to compare the free energy of the unbound state to the free energy of the bound state, which is what you need to do in order to assess, like, how well does a particular drug bind to a protein. You can now use, that's a physical free energy difference, but you can use that particular analogy now to actually train a diffusion model to get this molecule and move it onto the protein and compute the free energy difference. And that's beautiful that you can sort of use the same math in one method.
Amazing and fantastic. And maybe it's the final question, like, for this audience, yes, are like the people from industry, from academia and startups, and you were successful in all of these fields, actually, academia, industry like Microsoft, and your startup is one of the most funded startups in Europe. And you actually do a lot of impact with your AI. So for the audience today, like, do you have any advices? What areas to look at and to actually bring the most impact today? Like, what will be the best areas for that?
Okay, so there is obviously a lot of activity in chatbots and LLMs, but that's a race that's more or less run, I would think. But you would have to look what's the next thing. So I would not go quantum at this stage because it's too far out. But as I said, I think robotics and physical AI will be the next thing. So we'll put AI in every physical device, going from not just from phones, but in cars and humanoid robots everywhere. And of course, also in experimental facilities and everything. So combining physics and things with AI and thinking about the interface, making the interface smooth, I think is what's going to be next on the menu. And I think that I would put my effort there, which is what we're doing, of course.
Yeah. Thank you so much, Max.